here. Okay. So more with continuity. Some of this is going to seem silly and repetitive, but then you're going to see we're going to get to kind of one that's very thought-provoking here. Finding the x values at which f is not continuous, which of these discontinuities are removable. So pretty straightforward. Where is this not continuous? Okay, so at x equals 5. It's not continuous. Just, what's the reason? Jump, okay? So essentially, the real reason for not being continuous, knowing that continuous means that the limit has to equal the function value. This particular one is discontinuous really because the limit doesn't even exist, right? If the limit does not exist at 5 because of the jump, continuity is off the table, right? Continuity isn't even a possibility. And really, when that's the case, when your limit doesn't even exist, it's not continuous. And those are really your non-removable ones. Non-removable. Okay, on the second one, piecewise functions. Again, we've done these before, but just let's look again. In this interval, okay, strictly when you're looking less than or equal to 2, this is just a line. So that's always continuous, yes? So within its interval, we don't have to worry about it. And this one's a quadratic. So within its interval, we also don't have to worry about anything. But at the changing of the intervals, at 2, we have reason to be concerned. So before we kind of look at continuity, let's see if the limit even exists. So the limit as x approaches 2 from the left, and the limit as x approaches 2 from the right. From the left, we're using numbers less than 2, so that would be equation 1. So plug in 2 there, and you get negative 4. And then 2 from the right, if I plug that into this one, 4 minus 8 is negative 4. Negative 4 plus 1 is negative 3. So again, continuity is off the table. We can't even get to the second item on our checklist of continuity if the limit doesn't exist. These are different, so the limit as x approaches 2 does not exist, therefore discontinuous at x equals 2. And visually, what happened there? What happens at 2? Is it a hole? Is that why continuity isn't existing? Right, it's not a jump function, but it is a jump going from one linear piece to a parabola, something like that. So it is a jump of sorts. Okay? This next one's where it gets interesting and kind of stretches you to the next level, because your intervals are not just about x, right? Not x is less than or equal to 2 versus x is greater than 2, but rather the absolute value of x minus 3 is less than or equal to 2. So I think the first thing we have to do is figure out what just the x value situation is. So thinking back to solving absolute value inequalities, how do you solve this? And again, this is kind of one of those lost topics when it comes to the Common Core. You didn't do any of this in Algebra 2 at all. We did it really in almost, it felt like in passing in pre-calc, so I would assume that, I'll just assume you don't remember it all. With absolute value equations and inequalities, they sort of branch off into two different scenarios. And for inequalities, one you keep exactly the same. X minus 3 has to be less than or equal to 2. Or x minus 3 could be greater than or equal to negative 2, where you flip the direction of the inequality sign and you flip the negativity. Do you remember this? Okay? So when I solve this, add 3 to both sides, x is less than or equal to 5. And when I add 3 to this side, x is greater than or equal to 1. So this statement is the same as saying we'll follow this first function when x is less than or equal to 5, and again when x is greater than or equal to 1. So really, when it's between 1 and 5, does this make sense? When x is less than or equal to 5 and x is greater than or equal to 1, essentially that is when x is between negative 1 and 5. That's really what that is saying. Everywhere else, which is going to be anytime x is less than 1 or anytime x is greater than 5, we're going to follow the second function. Good? Okay. So between 1 and 5, that's going to be any time we're taking the cosecant of pi over 6 up until 5 pi over 6. Are you with me there? Plugging in an x of 1 and plugging in an x of 5 would lead us to thinking about what happens between pi over 6 and 5 pi over 6. So if you think about the cosecant of all of those, again, of course, another wrinkle, they're using cosecant and something that's less familiar. This is the same thing as 1 over the sine of pi x over 6. So are there any issues of continuity that are going to come up? We have asymptotes at an x value of 0. Does that affect this? No, because based on this interval, we're not looking at anything less than pi over 6. So 0 is a non-issue. When else would this be undefined? At an x value of, if sine is pi, yes, but what would x have to be to make this pi? 6, exactly. An x value of 6, but that's also not the interval that we're using this equation anyway, right? Because an x value of 6 would make this 6 pi over 6. We don't have to worry about that. We're only looking in between here. So yes, the cosecant would be undefined here when x is 0, not in our interval. And yes, the cosecant would be undefined over here at pi when x would need to be 6, which is also not in our interval. So in between these two numbers, this cosecant is always continuous. You follow? Okay, so even though cosecant has a boatload of discontinuities, if x were 0, if x were 6, if x were 12, if x were 18, but none of those fall in this interval. So we don't have to worry about discontinuities within here. Anywhere else, we're using this other equation. Okie doke. So the only place we have to worry about is what happens really at 1 and 5. Where we jump when x is 1 versus x is 5, where we jump from this equation to this equation. So let's think about our limit as we approach 1 from the right. And let's think about our limit as we approach 1 from the left. Okay? If you're approaching 1 from the right, we're using the top equation. Agreed? Agreed? 1 from the right? So what is the cosecant of pi times 1 over 6? So that's essentially 1 over the sine of pi over 6. So I'll kind of do it out and show all the work. Which is 1 over the sine of pi over 6. And what is the sine of pi over 6? A half. What is 1 over a half? 2. And then what is the limit as we approach 1 from the left? That's this equation. So that's 2. So does the limit exist as we approach 2? Yeah. Yes, you're right. I'm sorry. Thank you, Josh. Does the limit exist as we approach 1? Yes, it's 2. Okay, so the limit exists. Is it continuous there? What is f of 1? F of 1 would mean we use the first equation, right? Because when you plug in 1 minus 3, 1 minus 3 is negative 2. Absolute value of that is 2. 2 is less than or equal to 2. So when x is 1, we're using the first equation. And we already plugged that in, and it had a value of 2. So the limit exists as we approach 1, and the function value exists, and they're all the same, so it's continuous at 1. The other place of emphasis is 5. So the limit as we approach 5 from the left, we're going to look at, and the limit as we approach 5 from the right. Well, 5 from the right's easier, correct? It's just 2. 5 from the left, we're using the top function, so let's plug in a 5, and I'll just go right to 1 over the sine of 5 pi over 6. Still 1 divided by a half because we're in the second quadrant. Sine is still positive there. Reference angle is pi over 6, so it's still a positive 1/2 denominator. Still 2. And then f of 5, still 2. We already evaluated that in the first equation. So this thing has no points of discontinuity. It's continuous everywhere. Okay, now let's take a look at this function just to you really can't. I'm going to graph both of them. 1 over the sine of pi x over 6 and 2. And my window, I'll go, my interesting places of conflict are 1 and 5. So I'll go negative 10 to 10. I think I'm in degrees because I worked with some geometry kids. Okay. Okay, so I'm just going to freeze that because. So, at 1, between 1 and 5, we're following the secant graph. So from here to here, we're following the secant graph. Because when x is 1 and all the way up until when x is 5, that's when the absolute value of x minus 3 is greater than 2. Okay, I just totally threw a wrinkle at it by using those letters. And then everywhere else, we're following this. So you can see this. Yeah. Okay. Nasty little problem. So that was homework that you do tonight. I just was like, I know you always do the odds. I just was looking at some of the evens and I thought, ooh, when I looked at that one. So just definitely a more advanced type of question, but a good discussion. Okay? Continuous everywhere. Next exercise. Obviously, an E scares us all, right? But this is just an exponential function. This has no places of discontinuity. Any x value is going to be fine. No undefined possible. So certainly, obviously, anytime x is greater than 5, we're still not going to have any discontinuities within the interval to worry about. This is linear, so no discontinuities to worry about. So with a piecewise function, It's the point of transition that's worth considering. So the limit as we approach 5 from the right, and the limit as we approach 5 from the left. And before we can talk about continuity, let's see if the limit even exists. So 5 from the right is the top equation. So if I plug 5 in, what's 5 minus 5? E to the 0 is? 3 times 1 is? 10 minus 3 is? 7. 5 from the left, go in here. The 3/5 times the 5 is going to cancel the 5, so it'll just be 10 minus 3, which is 7. So the limit exists because they match. And the function value at 5 obviously exists. Sometimes that seems like a silly piece to check with piecewise because you kind of already did it if you did the limit from that side, but just show it so that you're really confirming that the limit as you approach 5 equals the function value at 5, which we would use this equation, which obviously again is going to be 7, and so this is continuous everywhere as well. And all real numbers. And then the last one is going to be done less from an evaluating perspective, more of just, you know what these graphs look like. These have jumps all over them, right? At any integer. So this is going to be discontinuous at all x's that are elements of the set of integers. 0, 1, 2, -1, -2, -3, and so on. Okay, if I do 5 minus my greatest integer function, x, and go from like -5 to 5. At every integer, there's a step. I even missed them, but they continue and it just jumps at every integer. Okie doke. All right. This are skills that have come up via multiple choice questions, but on your homework, it really gets addressed in an entire section. We want this to be continuous everywhere. Well, again, this is an exponential function, so on its own, this is continuous everywhere anyway, so certainly less than or equal to 4, it's still going to be continuous. Log functions are not continuous everywhere, right? This one is only continuous beyond 3, agreed? 3 would give you a 0, which would be a problem, and anything less than 3 would give you a negative number, which would be a problem, because we can't take the logs of those types of numbers. But anything greater than 3, this is fine, and this is only restricting it to greater than 4 anyway, so we're fine. The question of interest is what happens at 4, and we want to find the a value that's going to ensure that this will be continuous at 4. So in other words, the limit as we approach 4 from the left has to equal the limit as we approach 4 from the right. So approaching 4 from the left means we have to plug in 4 to this equation. For what variable? We plug 4 in for x. So 2e times a to the a times 4 power minus 2 has to equal the natural log of, and we're plugging 4 in for x down here as well. So 2e to the 4a minus 2. This is the natural log of 1. Goodbye. Have a good weekend. The natural log of 1 is 0. 0 plus 16 is, oh no, the natural log of 1 is, oh yeah it is, natural log of 1. E to what power gives you 1? 0. So it's 0 plus 16, which is 16. Thank you. Okay, thank you. And then we just solve that. Add 2 to both sides. Divide by 2 on both sides. Take the natural log of both sides. I'm solving for a here. So 4a equals the natural log of 9. And just divide by 4. So a equals the natural log of 9 divided by 4, which will be some crazy decimal, but multiple choices will present it in exact form. Okay, so finding missing values that will make it continuous. That'll make 4 from the left equal 4 from the right. Okay? Continuity of a composition. Okay? I think it's easiest to just write the new function. So f of g of x equals. And when you're doing compositions, you're literally taking the g of x function, in this case, and plugging it into the f function. So that'll be 1 over the square root of x minus 1. So there's two things here that would cause a problem. A denominator of 0. What x value would make the denominator 0? 1. So x cannot equal 1. And the radical, because you can't take the square root of a negative. So what values would make us be taking the square root of a negative? Anything below 1. So x cannot be less than 1. What's the better and more concise way of saying that? If x cannot equal 1 and x cannot be less than 1, then x has to be greater than 1. So this will be continuous for all x's greater than 1. And just for the fun of it, let's take a look at this function. 1 divided by the square root of x minus 1. And there we are. For all values greater than 1, it's continuous. Okay? And then lastly, because it's going to come up, do you know what arctan means? Okay. When did you learn that? Physics. Same. Liam, physics. Josh, physics. Okay. It means the same. I mean, you've done it before. You just don't know. It means the same thing as inverse tan. It's just in math we use that notation more often. Or I don't even know if that's true. We use it certainly in Algebra 2. That's what we use, and we use that this year. Arctan just hasn't come up yet. So if you see it, that's what that means. So if we, just to back up, how do you evaluate this? Right, you're pretty much looking for a tangent of what angle would give you root 3. And what's the answer for that? Okay, that's one of an infinite number of answers. What else would give you root 3? 4 pi over 3. What else? Okay, so you gave me the one before that. Let me kind of show people what you might be thinking. All students take calculus. So anything where tangent is positive, first of all, so these quadrants are out. And the reference angle has to be pi over 3. So 1 pi over 3, 4 pi over 3. Keep going. This would be 7 pi over 3, right? What do we keep adding on or subtracting to get from one of these to the other? 3 pi over 3, right? 1 pi over 3, 4 pi over 3, 7 pi over 3, 10 pi over 3, which is what? What's 3 pi over 3? Pi. That's the period of tangent. That's why you keep... So any x value that's pi over 3, add pi any number of times. Or subtract pi any number of times. And you've got all of your answers there. You just have to say where k is an integer, or where k is an element of the set of integers. That weird capital Z is really the more mathematical way of writing it. So k could be 1, and you'd add on pi just once. Or k could be -1. That's where Liam got his -2 pi over 3 from. he took pi over 3 and he subtracted pi. So he subtracted 3 pi over 3, which got him to negative 2 pi over 3. So k can be any integer, positive or negative, obviously. That's what the definition of integers is. And then you've got all of your answers. So nothing new and crazy, just a different way of presenting it. If you see arctan, the same is true for arcsine or arccosine. Honestly, in calculus, you see arctan, arcsine, and arccosine a lot more. I don't know why that notation as opposed to the inverse notation. That would be a great question for me to ask Mrs. Hill. I don't know if she would have an answer as to the reason why, but it is definitely more common to see that in calc.